All right. Good morning, everybody. It is a pleasure for me to be here. Thanks for sticking out of the last day of this fantastic meeting. Actually, this is my first in-person talk at ELS, so I'm very honored to be giving this talk. My name is Cesare Grava. I am an astronomer, planetary scientist at Southwest Research Institute in San Antonio, Texas. I'm the project scientist of LAMP, and Kurt Rutherford is the principal investigator or PI of the instrument. And this talk is focused on the science that can be done with the LAMP, in particular for the exosphere. So I'm going to give you a little overview of the exosphere and how the instrument operates. Okay, yes, okay. So this is an artist edition of my favorite artificial satellite, Lunar Reconnaissance Orbiter, LRO. In the background, one of my two favorite natural satellites, the Moon. And LAMP is here. Is this about a shoe side box instrument spectrograph, which is pointing at the lunar surface in good company with the Vanner, LROC, and all the other 6 LRO instruments. So it is UV or FUV, extreme ultraviolet or far ultraviolet imaging spectrograph. So this is a it's not a spectrometer, meaning that it can collect all the photos from all the wavelength from 570 to 1970 angstrom. And the LAMP is an acronym, stands for Lyman Alpha Mapping Project. The main goal is to study the surface properties, the properties of the surface of the Moon, especially porosity, hydration, mineralogy, and volatiles in and out of the PSRs. And so how can you do that? You can observe both in the day side, using the light from the sun, of course, reflecting off the lunar surface, and also on the night side, especially doing in PSRs. So how does it do that? It uses direct illumination in this case, which is coming from the stars, UV bright stars. They shine onto the surface of the Moon, and the light is backscattered to the instrument. And also interplanetary medium, so in particular interplanetary hydrogen atoms, is interstellar medium basically flowing through the solar system. And if you wear like a pair of goggles in the UV, you will see like sort of a diffuse halo in the sky. So there's a door. So when we cross from the night side to the day side, we close the door so we don't burn the instrument, and we let the light pass through a smaller aperture. Okay, so it is a very sensitive instrument because the main goal is to study the lunar reflectance in the UV, and nobody has done this kind of work actually, using the light from the stars to study the properties of the PSRs, for example. So it is so sensitive that it is suitable to detect the faint emission line from the lunar exosphere. And it does this in 3 ways. So one is the simple needy observation, so riding along the spacecraft, pointing at the surface. You can get emission lines from the exosphere when the exosphere below the instrument is illuminated and you're looking at the night side of the Moon. This happens every orbit, but only in the poles where the spacecraft is crossing the terminator, and there's enough light, enough gas illuminated between the instrument and the surface. To get measurements of mid-latitudes, then we need to move the spacecraft. We have to call the LRO MOT, say, hey, can you please slew the spacecraft? And so in this case, we are still looking at the night side, like a reading on the terminator. And the line of sight is longer, and you can measure also light from here in the mid-latitudes. And also another example is stare at the sky, so 180 degrees up, and you measure all the column gas from the instrument to infinity, basically. So, okay, let's start with the helium. It's the brightest element we can measure with this instrument. It is at the emission line at the very edge of the detector, extreme ultraviolet, so 584 nanometers, and angstrom, and it is very bright, relatively bright, so we can detect it in the first few months of the mission. So the main source of helium is neutralization of solar wind alpha particles upon impact on the surface. And it was proposed during the Apollo measurements by Hodges and Hoffman. And we did observations with the lamp. Okay, so again, this is not shown here, but okay, so on the y-axis is the surface density that we measure with the lamp, so neutrals in the exosphere, and so the points. And the line is the measurements of the solar wind alpha particles coming into the moon, measured by the Artemis. So Artemis, capital letters, not the Artemis, the program, is Artemis, a twin spacecraft. And versus the day. So if you look at the monitors there, you can see there is a gray area here. It is where the moon enters the geomagnetic tail. In this case, basically, the moon is entering the Earth magnetosphere, which shields it from the solar wind. So you turn off the solar wind, basically, and what you see is a decrease in the neutrals with the exponential decrease, because it's really immediately lost. It's very, very fast escape. And there's another component of helium which is interesting. So it was recognized even from the so for the Apollo I think it was 15, 16 orbital alpha particles mass spectrometers, that there is ongoing outgassing on the moon. So these instruments and also the Kaguya alpha particle spectrometers measure the alpha particles from the radioactive decay of radon and polonium, which are results of decay of uranium. And also the LACE mass spectrometer during the Apollo 17 mission measured argon 40, which is not the dominant argon 36 you see in the solar wind. Is really endogenic. It's coming from the decay of potassium 40. And so if these gases are present on the moon, there may be other gases are outgassing. And helium is one of these, is the product of the decay of thorium and uranium. Okay, so with the same instrument, we plotted the data in different ways. So we measure, so in this case, on the y-axis is the measurements from LAMP, so neutrals in the exosphere. On the y-axis is the measurement from Artemis or wind alpha particles. You expect a linear correlation if they are correlated, which is what we see, but it's not a one-to-one. So we made a fit to this relationship, and we found out two important parameters. So the slope of the fit, or actually the inverse of the slope, 1 minus the slope, is the amount of helium that we are not, it escapes the moon undetected by LAMP, maybe because it's, I don't know, too fast or in some other form. And the intercept gives you an estimate of the source rate you have if you turn off the solar wind, basically. So you go to the 0 of the x-axis, there's no solar wind, and you still see some helium. That is the endogenic component. And this flux that we derived is corresponds to about 20% of the solar wind. So not a negligible contribution. The second species we detected was molecular hydrogen. It took more time to accumulate this because it's fainter, and we detected from the Lyman alpha and Venner bands in the far ultraviolet region here. So this is, we also found a dawn-dusk asymmetry. And basically, the measurement of molecular hydrogen gives an idea of the contribution of solar wind in the production of water on the moon. So in this case, there are protons that impact the lunar surface, and there are different pathways for these protons to interact. So they can interact with oxygen atoms to create oxide, or like OH or hydroxyl, or can create nanophase ions, or can just neutralize the atom, hydrogen atom, and then the next one, hydrogen atom, can combine to form H2 and then diffuses. So by constraining the amount of H2, we can, in modeling, we could find that, for example, the strong chemical sputtering is a dominant source of exotic H2. Okay, so we did place upper limits on other species. In some cases, like in the magnesium, is 3 orders of magnitude lower than the previous upper limits. So that is pretty interesting investigation. And let me conclude with the dust exosphere. So there's not only atoms, it's really dust. And so the long wavelength of lamp is particularly sensitive to 2 types of scattering. So in this case, forward scattering of sub-micrometers size particles. And so we, in this case, for scattering means you are looking towards the source, so the sun, and the particles are forward scattering towards you. And so we had to observe this dust exosphere when LRO was in shadow, looking at the terminator, and the sun was here just below the horizon. And we place one upper limits from this type of dust, which is about 100 times smaller than what was inferred by the Apollo 15 coronal photographic images. And the other population of dust is a nanometer size. Again, the same long wavelength is sensitive to, actually now it's a back scattering of nanodust particles, so smaller particles, and we're looking with the sun on our back. So in this case, we kind of reproduce the observation by LADI UVS, who detected the population of dust. So looking, the sun is on the back, we're looking at the night side, but still on illuminated column of dust. And we find, again, upper limits were 100 times smaller than what the LADI UVS estimated. So this is an interesting discrepancy, and we're not sure what's going on, maybe the different environment parameters, or there are other hypotheses we discuss in our paper. Okay, so conclusions. LAMP demonstrated the advantage of performing exospheric science on the moon through UV and FV imaging spectroscopy. Combining this with other detections, like, for example, the atomism in the particles, we can constrain, for example, the endogenic source rate from the interior, and then giving clue information on the moon. And this can be applied to other solar system bodies. So the exosphere actually is the most common atmosphere in the solar system. So most of the objects, the medium, large size, have an exosphere. Even the Earth has one, started at 500 kilometers altitude, but not only the objects that have an atmosphere. So this gives really an idea of how these bodies, so Mercury, the Moon, Ceres, react to the change in the drivers, which is solar wind or meteoroid impact vaporization. And there are tons of other scientific results on the surface science, but I'll give that to next ELS probably. Thank you for your attention.
Okay, thank you very much. Do we have any questions for Cesare? Oh, we've got one at the back.
JPO. Cesare, nice talk on all the UV capabilities. For the dust detection or lack thereof by UVS compared to LADI, were they looking at different altitudes? Is that a possible explanation? One seeing different heights?
Yes, possibly. In fact, if you see the geometry, they had to look farther away from the moon than we did because we detected the emission right from the instrument. But yeah, it could be, but it should be the opposite if that were the case, right? Because we observe closer and brighter emission lines. So I don't think that should be the cause.